My coworkers, Vladimir especially, who is the principal work in this topic. They are all based in Netherlands, while I'm local here in Denver. So I had the honor of presenting here. Uh, okay. So as we first talked about, like for last 3 days, we have been talking about all the work that goes in delivering the end-to-end workflow. Let's say we do all that, we deliver the content to the end users, but we have fairly sophisticated pirates, as Chris showed in his slides. They will leak the content uh, and sell it for cheaper or just, yeah. And once that happens, how do we trace it back? Or at least if we can trace it back, we can think of the next steps. Like, do we ban them? Is this pirate some college kid? Is this someone's credentials which got stolen? Or is this a part of a really sophisticated criminal network? And one of the options to trace it is to use forensic watermarking. Uh, at least in this paper and in our presentation, I will be talking about the AB watermarking. In AB watermarking, you create two uniquely watermarked copies of content, whether it's a WAR content, file-based, or single file for distribution. And each end user gets a unique combination of these A and Bs. So let's say if I'm one of the users, I will get A, B, A, B, A, B mixture. Someone else might get B, A, B, A, and so on. And then once the content is leaked, you can take the content, run it through the watermarking detector, retrieve the pattern, and then you say which user this pattern corresponds to. And all this this patterns I was talking about, the A and B combinations, let's call them the switching identities. There are different companies, different groups use different IDs, but basically this A-B switching is happening based on a binary pattern. And in this paper, in this presentation, we'll be focused more on these identities. For example, if you have, ideally, we wanted these identities to be built on the fly, mainly because, as Chris was mentioning, a lot of the watermarking claims and a lot of watermarking info is included in the token, and you want the CDN edge node to derive it on the fly. There are a lot of amazing classical methods, and we actually started with some of the Tardosh-based methods. They have great properties, they have great collision resistance, but sometimes they are very difficult to generate on the fly, and you need to rely on very complex lookup tables, a lot of caching. Another option was, or another thing we wanted to have was, let's say if you had 1 billion users, even running the detection and matching the payload that you have extracted, that pattern, and matching it to all the billion users is a time-consuming, memory-consuming process. So we wanted the IDs that can be easily partitioned. And and so the whole purpose of this is, especially for a live streaming event, if a stream gets leaked, we want to be quickly able to run the watermarking detection, identify the user, and if possible, try to take the stream down. Because in our current experiences, what we have seen is if one pirate network is redistributing the stream, if you take one down, whole bunch of these other IPTV apps will go down because they are all sharing the content, credentials, URLs, and whatnot. And that was the main purpose of the presentation. So I will show some results where we add, while we are going from some of these classical methods to this simple or a simpler uniform method, we still wanted to make sure that the system remains bulletproof for collusion attacks. So collusion attack is when you have bunch of these mouses, they collude together, they share each other's streams, run some combination, like either interleave the frames, segments, or even combine each frame together and retranscode it. so that they will try to defeat the watermarking, basically. And so we wanted to test up to like 25 colluders on a 1 billion user set. Like that was our goal. Here is we want to recognize all the background in this topic. So the traitor tracing literature has been around for a while. We particularly started with the Tardosh methods. These are, in this case, they use probability-based algorithms to generate these switching IDs. So before I go further, I want to kind of give an overview of how this A-B watermarking works. So as you see up there, you will have the A and B combinations. So the embedder is creating A and B copies. And during the switching phase, you are getting like a B1, B2, A1, A2. So that's how each user gets a unique combination. All that switching will happen on the CDN edge. That's a very reliable method to do it. And all the information that you need to do this switching will be carried in these either common access token, JWT, or any other method. And if you see the diagram below, that's like a simulation of how a group of pirates can work together and create a collusion attack. So there are like frames in different colors. So one of the simplest attack will be like each one gives you one segment, you combine the segments together. You can do a frame level attack. You can actually decode all of those 5 streams and do an averaging of all the pixels and create another transcoded stream also. And basically, we want to make sure that the algorithms we use can preserve such collusion attacks. So as I said, some of the traditional methods, like the Tardosh methods, it was very, so let's take one practical example of like if we had 1 billion users, based on our simulation, we found out that you will need around 44,000 bits to be able to find 25 colluders. This is a theoretical extreme, but we wanted to make sure that we can still survive that type of an attack. Just that whole detection acquisition process will require 5 terabytes of dynamic memory. And that's why we wanted to have a ID generation scheme where we can partition them in different sets and do the math on each partition. In order to be able to partition the data, so I was talking about those probability-based methods for Tardosh. So if you see the curve here, the line in green, that's how a particular bit, like what is the probability of a particular bit to be 0. So the Tardosh codes try to achieve that kind of a probability curve because it has a lot of benefits in detecting it is actually robust when a lot of colluders are acting together. But the cyan curve that we are showing, that's a curve that you will achieve when you use a very straightforward method like a AES CBC encryption to generate the switching IDs. And when you have that type of probability distribution, it's a lot easier to split the entire, like 1 billion users into multiple partitions, and they all have fairly similar statistics. So in the plots, we are showing that pretty much all of the partitions will have the same, have an average of 0. There is a standard deviation is roughly same. And that's why a threshold for finding the correct match, one of the users out of the all the users that are in the database, we can, so if a user, so let's say we ran this acquisition scoring for all billion users on one machine, the, let's say the 4 users, if they were the colluders, we also want to make sure that if those 4 users belong to 4 different partitions, we will still be able to catch them based on the math we are following. And even talking about the math, I was talking earlier that once you detect the watermarking pattern, you are comparing it with all the users. And when you do this comparison, like if you have just 4 bits, you can do it manually. But if you have billion users and a code word which is like 40,000 bits, you need to use some sort of a math. So when you have a uniform distribution, you can use a very straightforward penalization method where you just, when a bit matches, you get +1, when there is a mismatch, you get -1. For Tardosh methods, they also recommend to use the right probability for that method. And so that if a bit had a low chance of having 0, then you should get higher score when that 0 matches. Again, the approach is very sound, but in order to scale it to a large user set, we need to then have all these probability tables. I have like 3 minutes left, so let's jump into some of the results and simulations. So this is the summary of our test set. Like we tried to have up to like 100 million to a billion users. Our length of our code word in our simulations was 32K to 43K. That was the, in order to get 25 colluders in a set of 10 to 100 million users, we needed to have 32K code words, 32K bits. In a set of 1 billion, we had to increase it to like 43K. Like these were all the simulations we were doing and coming up with these numbers. I had some, oh, this is working. This is good. So this is a case of, because when I tried yesterday, it wasn't. So I had some backup. So in this case, this is the ideal case. When, let's say, if I was the colluder and I leak the content, I will be the one with the blue line. My score just keeps increasing. And for every other user, as soon as a bit mismatches, they will get a negative score. So if you see the pink line, that's where all the rest of the users, their scores will be below that line. My score keeps going up. And typically, in maybe 30 to 40 bits, we will be able to find a correct match, and you can then stop my stream. Now let's look at the case where we had 2 colluders. All of a sudden, you can see that it takes longer. Now you require like 100 bits or so, and after that, only 2 users, their score keeps increasing, everybody else is below the threshold. Now you can safely say that, okay, you can still detect 2 users, it just took longer. Now we go from 2 to 5. Again, it takes a little longer. Now you required, so you see like 1 user actually went above the threshold after like 1,500 bits. So now you're looking at close to 1,500 to 2,000 bits. And the last one was the most challenging case. This is the 25 colluders in a user set of 1 billion. So this will keep going. It will take its own sweet time. But after around like 30,000 to 32,000, I think in our simulations, we were able to get, I think, 24 out of 25 directly using like our threshold-based scheme. Only for one case, we had to do some manual analysis on one of the partitions. Okay, so as you see, this animation keeps going. So the 25 scores, they go above this threshold. And last, here is just some summary. So some of the classical literature had given some estimates of a theoretical limit of how many bits you will need to have like 25 colluders. And our hope was we will be below this, but we are well below it. Again, these are theoretical max. I don't, hopefully, I hope we don't ever have to deal with a case of 25 colluders, but if we ever have to, we wanted to make sure that we are ready, just in case. That's all I have. Thank you for sticking around.
Thank you. Do we have questions? I do actually have one. So, thank you for the work. It's very interesting. I'm just trying to put it in practical terms, because even with 5 colluders, so you said you need like 1,500, 2,000 bits.
Yep.
So how does that relate to effective time? Because my understanding at least is that this is like the A/B patterns that you need to detect. So that would mean you have an actual live stream with 2-second segments.
Yep.
So 2,000 bit means you need to watch the entire football game.
You need to have like almost a couple of hours of it. So that's why if you have a very sophisticated attack, that is more challenging. But if we can go back, let me see. If you kind of pay some manual attention, like if you have some resources to watch it, you can see that some users, their scores start creeping up. And the hope is, let's say in a current football match, you are not able to find anybody. Or let's say you are able to find people, but we're not able to take any enforceable action. At least you have some forensic data. You can at least put them on a watch list. And if you see some same groups doing this pattern again and again, so you have to build the intelligence over the time. But if you at least have some watermarking, then you at least know whom to keep an eye on. Without that, then you are just trying your best guess.
Cool, thank you. All right, let's give it up one more time.